Okay, so let's continue talking about muscle physiology, and we're going to talk specifically here about the motor units. If you're following in the textbook, this is going to be on page 84 of the Levangie textbook. In terms of the motor unit itself, there's some good visual pictures here. So here's the picture from the last lecture, the last PowerPoint. You can see the actin myosin there. But how do we get to there? Well, we have this nervous system, central nervous system, that's going to transfer to the peripheral nervous system and then send the signals down there. So this motor unit, when we talk about the motor unit in particular, we're really talking about the motor neuron for the alpha motor neuron. And this alpha motor neuron is going to innervate, you could see, multiple muscle fibers. There's going to be quite a high number of this. So when the motor unit receives this stimulated through the alpha motor neuron, it's going to create this cascading chain of events. And so part of the ability of strength is the capability of our nervous system to send these signals at the appropriate times. Consequently, if the central nervous system or peripheral nervous system is sending these signals inappropriately, you could have increased tone or increased spasm. And so you can maybe think of cerebral palsy or Parkinson's or other things like that. We have tremors or other spasticity or extra muscle contractions. We do know these vary greatly per muscle. For example, the gastrocnemius has 600 units that each innervate 2,000 fibers. So it's just an amazing amount of number of these units within our body. So you can see how intertwined the system is and how many different units could contract simultaneously. It's quite amazing. Now, of course, there's different types of these muscle fibers, and different muscles have different orientations or dispositions for these. But just to kind of show you where we're at, I mean, there's the overall muscle and the myofascia there. There's these fascicles. Within the fascicles, there's these groups of muscle fibers. And then here we are here, thick and thin filaments. So it just gives you a representation. We're talking about the group of myofibrils, which is a group of myofilaments right there. So we have three main types. There are going to be some different terms thrown around. It's not as simple as there's type 1, type 2, type 3, but there is type 1. And typically when we think of this, we think of these as our slow twitch. Sometimes they're known as slow oxidative. You may hear that term. So that's one. You have your type 2. Now there are typically two type 2s, but when we think of type 2, we think of fast twitch. So when you have Dolph punching there, it's going to require obviously a lot of fast twitch fibers, type 2. And there are two different versions or variations in type 2. And so how they divide these. So there's your 2As and your 2Bs. I forgot a little 2 there. Okay, so your 2As and 2Bs. So with this, your 2B, and sometimes you will see this referred to as 2Xs. So that's a thing in medicine. There's a lot of different variations for how these things are defined. But you got your slow twitch and your fast twitch. Now, your 2As are sometimes called intermediate, and they are a combination. They're almost this hybrid between your slow twitch and your fast twitch. So slow twitch, and this gets down to energy consumption, your slow twitch are going to contract more for endurance. They're going to contract repeatedly a lot of times throughout the day. And so when we talk about energy source, what's readily available to our cells throughout the day? Oxygen, oxidative. So to take oxygen, convert that through ATP and so forth to provide energy, that's going to be our slow twitch. Our fast twitch are going to use some type of glycogen for this, glucose derivative. So with that, the 2As are going to do a little bit more of a combination. So they're going to use glucose, glycogen, but they're also going to use somewhat oxygen to a certain degree. So they're like your hybrid type, but they're still considered fast twitch because they're type 2. And then your 2B or 2Xs, they're going to be the largest diameter. They are, in terms of color, they are the lightest color, so they are your white type color. They have very poor blood supply, and they fatigue very easily. So they're not very efficient, but when they do contract, they contract very forcefully. So they use a lot of horsepower when they contract, but they can get some great contractions, and they're really important for power and speed, jumping, running, punching, those types of activities. But they're also very important for fall risk patients because we need those muscles to contract quickly. So we're going to talk more about this, but let's keep moving on to the next slide here. Characteristics. So we have these 3 different fiber types, but are these evenly distributed? Is it just 1/3 type 1, 1/3 type 2A, 1/3 type 2B or 2X? No. As you can imagine, there are different distributions for different muscles. As we talk about this, I have the picture of the turkey. Getting hungry looking at this now. But with this, if you think about turkey and you think about light meat and dark meat, those are your different variations of the fiber types as well. And if you look at a turkey, you can see in certain parts of the turkey, certain muscles, there's going to be more distributions of the dark meat versus the light meat. And so with that, and different animals also have just different distributions of that as well. Some other terms, because there's always multiple terms for things, is they talk about the dominance of this. So you may hear a muscle being more slow twitch dominant, made for more endurance. And so what we would call that is, you're going to hear if a muscle, let me get my cursor here, is more slow twitch heavy. So let's say a muscle is 80% slow twitch heavy, which is more for endurance. This would be more of a tonic muscle. And let's just go over examples. So thinking about that, what's an example you could think of in the human body that doesn't have to contract very forcefully, but has to contract a lot? And so I'll give you an easy one. So if you think about your neck muscles, supporting your head up, our heads are supported whether we're sitting, standing, walking around. Those paraspinal cervical muscles have to contract a lot, but they don't often have to contract very forcefully. With our heads, we don't lift things. Typically, we're not carrying things from side to side on our head, so they don't have to. A lot of the postural muscles, so we think abdominal muscles, erector spinae. I'm running into the turkey here. I better stop typing and think of muscles there. So with this, a lot of those postural control muscles are going to come into play here. Now, what about your fast twitch? So these are made for more power. I cannot spell here. Power and speed. Do you know what we call these muscles? Sometimes these muscles are referred to as your phasic muscles. So if you think of things that we do at a high rate or high speed, they can be more phasic in nature. So if you think about jumping, what are some muscles involved in jumping there? So your quadriceps might be more phasic in nature. And so we think, oh yeah, running and jumping and sprinting, that's going to involve more fast twitch fibers. But the other thing we know is that within the human body, there's differences from person to person. And naturally, we know that some people are more geared and genetically dispositioned towards fast type of movement. Can you jump high? Can you run fast? Can you do those types of things? So some people might have a greater distribution of fast twitch fibers genetically in their quadriceps than some other people. and other people might have more slow twitch. Sometimes when you look at running or marathon racing, you look at certain countries that have certain types of athletes. And so some of that could be genetic, but also some of that could be just training environment and cultural influences as well. So we tend to be able to identify that with our patients. And there's different ways to train slow versus fast twitch. All right, so we're working through this lecture, and I feel at this point you've earned it, a little bit of a cheesy joke, just to kind of break it up a little bit here. So let me get one out here. So here we go. Why did the golfer bring two pairs of pants? In case he got a hole in one. Da-da-da. Okay, so there we go. So that was your cheesy joke segment. Sorry about that. Let's keep going here. So the variations in fiber types among individuals are believed to be what determined? Often these are genetically determined. And then usually we say that once you've stopped growing, you've reached, usually younger for females versus males, but 16, 17, 18, somewhere in that age range when your growth plates have closed and your muscle is no longer developing, there are very few changes in fiber types. There are some people with certain amounts of research that believe that there can be some variations on that, and there might be, but certainly there's nothing to say are dramatic changes in these representations after a certain age. Now we can cause atrophy or hypertrophy of fast or slow twitch, and so we can cause that, and so we can take someone that has a lot of fast twitch and we can train them on more endurance activities to develop more of their slow twitch muscle fibers and cause some hypertrophy and more vascularity and other things like that for the slow twitch versus the fast twitch. Now, I do want to cause some attention here. So the quadriceps we were just talking about, the last one, has found to be 50-50. But keep in mind that this is going to vary from person to person. So there may be some people in the class that are 60-40 that are sprinters, and there may be some high endurance or long distance runners that are more like 30-70, and that's maybe why they've been successful at running, is so they have a greater distribution of slow twitch versus fast twitch. And the gastroc, there's some debate, and I do just want to call attention to page 86 of the textbook. There is a little bit of an error with that, so I've summarized that in Canvas, so hopefully that helps clear that up. So what typically happens to muscle fibers with aging? So thinking about that, what happens to our muscle fibers with aging? We know that our muscle fiber amount is generally fixed once we're in adulthood, but there are a few different things that happens, as you can imagine. One is they decrease in size. So with that, what do we call a decrease in muscle size? We call that atrophy, and there's some other terms for a decrease in muscle fiber size. So besides size, we also know there is a decrease in fibers in general, so we lose fibers. In particular, we typically lose the fibers that we don't use as much as we get older. So do you think that would be more type 1 or type 2? You can imagine that as we get older, we tend not to do activities that involve fast movements. Part of that is risk, and part of that is lifestyle. So generally, we lose more type 2 fibers. And so with this causes also a loss of ability to produce power or speed, or I should say a high speed of muscle contractions. We also have a loss of motor units. So when you do try and get a muscle to contract, there are less motor units available, so it becomes more challenging for individuals to contract that. Overall, we're going to have a loss of muscle mass as well. Um, and so this ties into this as well, loss of coordination. So I know I gave you more than 3 there. So there's a lot of different things that generally happen with muscles. But if you don't move it, you lose it. This has to do with the SAID principle. As we get older, as part of the normal aging process, we don't do certain activities as much, and we do other activities instead. And as we change our body lifestyles, our bodies naturally change as well. So let's talk about another term associated with loss. So penia, or loss or deficiency. So if you think of osteopenia, you probably think of a loss of bone. But what would be a loss of muscle? And we know that muscle is primarily sarcomeres. So sarcopenia, let me write this in for you. I'm a little off in my typing here, but so sarcopenia is the loss of muscle mass with aging. So here you go. So loss of muscle mass. Loss of muscle mass. Typically, we know that a large percentage of the body is composed of muscle. Sometimes you'll hear this as muscle mass, or some people refer to it as lean mass or lean muscle mass. Certainly, you could take the body and you could derive a fat percentage. So if someone was 10% fat, they would be 90% lean mass. Although that's somewhat misleading because you have the weight of the organs and bones and other things like that, which I wouldn't consider muscle. But typically, about 75% of the body is attributed to muscle mass, and as we get older, we significantly lose that. So starting as early as the 30s, and once again depends on lifestyle. This is SAID principle. Up to 50% of loss in muscle occurring by the 70s, and you can imagine certain muscles are more predisposed depending on the activity. So if you're doing less walking, less standing, less biking, you have significantly more muscle loss or atrophy or sarcopenia in the quadriceps and the hamstrings, etc. But your activities using your forearm may not change that much from, let's say, your 40s to your 60s. So you may have very little sarcopenia or muscle loss in your hand and forearm muscles. It just really depends on lifestyle as well. Do muscle fibers decrease in size or number with aging? What do you think about that? They actually decrease in both, but primarily in size. You get a shrinking or an atrophy of that, but we do know they decrease in number as well. So to get you some pictures, here's some examples of your slow twitch and your fast twitch. And with this 27-year-old female, you could see the size of that. Same area. So this was the vastus lateralis, quadriceps muscle, and they are stained to show that because they don't naturally occur like this coloration within our bodies. But you can note the changes. So what are some changes that you see there? So you could definitely see that there's a size difference. So look at the size of that. So there's that atrophy there. But do you see on the 27-year-old how many type 2s there are? So all the black ones represent the type 2s. And do you see there, I don't know, I'd say, this is just an estimate, maybe like 40% of these or close to half are type 2. Whereas look at the amount of type 2s and how much they've shrunk down. See, a lot of these type 2s are smaller than the type 1s now. So you could see you have a reduction in size, and in particular, they also have a reduction in type 2 muscle fibers from 27 to 67. Here's another representation here. So this is a cross section of right through the femur, looking at the different people, but 28. So you can see obviously the femur's there, intermedullary canal is right there. And so you can see the skin subcutaneous fat is right there, and then the muscle. And you really can't accurately distinguish quadriceps and hamstrings and everything appropriately, but you can see the variation in the muscles there on this picture. You can't see that, but what changed from 28 years old to 80 years old? You can see that the subcutaneous tissue is much greater. So there's a lot more subcutaneous fat and adipose tissue. Did the femur bone change that much? Now these are two different individuals, so that's hard to make that representation there, but you could definitely have a loss of bone mass as well. So it's reasonable to assume that you're going to have a loss of bone mass of the femur, but most significantly you have a loss of muscle mass. So that's a significant loss of muscle mass, sarcopenia, or atrophy right there. And then you get to this size principle of motor unit recruitment. This states that when we try to contract a muscle actively, we typically recruit the muscle fibers that are easier to recruit and they're more energy efficient, and those would be our slow oxidative. So we try and recruit type 1, and then once we run out of type 1, we recruit type 2. So if I were to have you do, I'll just say a squat, and I were to use a squat at a very low weight, you're going to use primarily your type 1s. But as I increase the weight more towards your maximum weight, or your 1 rep max, your 1 RM weight, you're going to need to pull in more type 2. So if we're at 50% of your max or 60% of your max, as I keep going up in number, I'm trying to get more type 2 muscle fibers. So this is also known as the Henneman principle. Henneman principle is the size recruitment principle as well. So just like our joints are designed in certain ways and shapes to allow for certain forces, whether it's first class, second class, third class, etc., we also have different shapes of muscles to allow for different force production. So when you look at muscle architecture, this is really the arrangement of the fasciculi within a muscle. So on the first one here, this is your fusiform muscle. So it has a fairly pronounced muscle belly, and then you have a tendon on each side. So when you think about your biceps breakout, either your biceps in your arm or your biceps in your hamstrings, either one is this typical fusiform development. And so with the fusiform, you can imagine that there's a lot of tendon that's covered here, and there's quite a lot of tendon injuries, tendinitises, with fusiform muscles. So that becomes something to mention. And then in terms of the pennation, or the arrangement, you have your unipennate here, so you can see the diagonal direction that the muscle is following here. This is your pennate. It kind of looks like a feather on one side, and so these typically occur with a lot of smaller muscles like your flexor pollicis longus. Some of the other hand muscles are in this pennate distribution. Then you have your bipennate muscles over here, so it's just like the pennate but just doubled up. It's like a mirror on each side. And then you have your multipennate muscles. So a multipennate would be like your soleus, your subscapularis would be another multipennate muscle. And consequently, there's not much trauma typically that occurs in these multipennate because they don't have a large room. So you can see there's not the large room. They also don't go through sometimes the same amount of atrophy or hypertrophy, either way. And then there's a lot of force on this tendon. So at this distal tendon here, there can be some trauma and tearing, but the fibers are a lower distance here, so there's typically not as much muscle fiber trauma there. And then another way to define muscles is by the motions that they do. So you've probably seen these terms before, so I won't spend too much on that. So you should definitely review these terms if you're not familiar with them. But your agonist, also known as your prime movers, Your antagonists are often on the opposite side of the agonist, but they could be on the same side of the body just doing the opposite movement. So if I'm doing elbow flexion, the biceps would be my agonist and the triceps would be my antagonist. There's also synergists, muscles that help work together for a certain motion. So if I'm picking my head up, there's certainly multiple cervical flexor muscles that come together and my paraspinals that help to perform that. There's also co-contraction. So as I pick my head up, I might have a co-contraction of my rector spinae or of my scapular muscles to stabilize other areas as well. And the last thing to leave you with on this PowerPoint is to just go over what are primary and secondary movers. I really like the kinesiology textbook, how it labels the beginning of each chapter for peripheral joints. So here's the shoulder chapter, and you'll see here in the sagittal plane, it lists in this purple color all the primary movers, and these are the ones we're most concerned with. So if someone has weakness with shoulder flexion at the shoulder, the deltoid, we're considering the anterior deltoid, the pectoralis. Certainly the biceps brachii and the coracobrachialis, they contribute to shoulder flexion, but they're very weak contributors. We're often not worried about strengthening the biceps for someone that's weak with shoulder flexion because it's a secondary mover. It's not as critical. Whereas abduction, supraspinatus is important, and middle deltoid is important. And some joints and planes don't have secondary. So you can see abduction, it only has 2 prime movers. It doesn't have any secondary movers. And then you look at medial or internal rotation. So it's definitely good to know the prime movers and secondary movers, but focus on the prime movers or primary movers at the beginning of each chapter for each joint that you're looking at. And that's going to be a wrap. We'll finish the rest of this up in class. Thanks, everyone.